I want to talk about electric motors. The idea is pretty straightforward. You have some kind of wire loop, and I have one here. You can see I have a square wire loop, and it's set up to rotate about this rotational axis. And we've got a current going through the loop. And if a magnetic field is applied to this loop, that means there are going to be magnetic forces on each side of the loop. Okay. Now, technically, it's at every single point along the loop, but we would treat each force as acting on the center of that particular side. So there'd be one acting on the center here, there'd be one acting on the center here, and here, and here. And those forces can result in torques. They can create torques. And that's indeed exactly what happens, and the wire loop will start to rotate. This is the idea. This is how electric motors work. Now, they don't use just a single loop. They use hundreds or even thousands of loops. But you apply a magnetic field that causes the torque to be applied to those loops. They start to rotate. The loops are wrapped around what's called the armature. The armature is what actually starts to rotate, and it's attached to the crankshaft or the drive shaft. And that spins, and that's how you're able to get your car to go. If you have an electric motor, an electric vehicle, then that's what allows the car to go. Or maybe it's a motor for an elevator, so it's able to raise the elevator or lower the elevator. It doesn't really matter. There's lots of uses, but this is the idea. Have a current going in a loop that is exposed to a magnetic field. Now, this diagram in this problem can be a little confusing, and that's because we're trying to represent three dimensions with a two-dimensional drawing. Okay. So I want to talk about this drawing a little bit, and to help me, I've got this simple little model I built. Okay. And so you can see here, here's the loop. I've got the corners labeled. There's point 1, or you could say corner 1, 1, 2, 3, and 4, and I've labeled them here on my little model, 1, 2, 3, and 4. Okay. And so that's pretty straightforward. And then notice up here there's this dot, the vantage point. And this second series of diagrams here, it says it's the view from the vantage point of wires 1, 2, and 3, 4. So this is wire 1, 2. This is wire 3, 4. So 1, 2, 3, 4. Okay, so the top and the bottom wires. So when we view these from the vantage point, which will be located here above my model, okay, what that means is I rotate the model like this. And now I'm looking at it like this. Now this is still corner 1, this is still corner 2 over here. And in the diagram, the current's going from 2 to 1 in mine. So the current was going this way. So when I view it this way, the current is still going this way. And you can see that here in the diagram, we still have the current going this way. Now this I23 and this I41, what are those? Well, in the diagram here, the current's coming up from 3 and going to 2. Okay? So it's coming up from 3 and going to 2. So if we look at it like this, edge on, that means it's coming out of the screen. So that's why there's a dot there. Over here, it's going from 1 to 4. So here's 1 to 4. It's going down this way. So that means we turn like this. It's going down. It's going away. So that's what's going on there. Now, what about this down here? Okay. Well, that would be if I just, now from this viewpoint, of course, we only see points 1 and 2. We can't see 3 and 4. But let's just assume we can cut these away. Now we can see these other points. We can see points 3 and 4 as a result. Okay. Well, guess what? The direction of the current hasn't changed. On this side, going from 1 to 4 was still going down. That's still the case. Still going down. And from 3 to 2 was coming up. It's coming up from 3 towards 2, so it's still that dot there. But now I can see this bottom part, and from the current was going from 4 to 3. It was going to the left, still going to the left. So I hope this helps you to see what's going on in this diagram. It was necessary to draw it this way so we could accurately show you how the magnetic field would be applied, but also so that you realize we do have a square loop. But you have to look at all the sides so that you can figure out what's going on. Now, the last thing that I need to talk about is torque, and specifically the direction of torque. I talked about this at the end of the other video in this problem, but I wanted to show you because there's a right-hand rule that applies here with regards to torque. So if we have simple bar. Here's the rotational axis. And if my force is applied like this, okay, so the lever, oh gosh dang it, sorry about that. The lever is horizontal in my diagram. So in this force here, it wants, if this is the rotational axis, it wants this bar to rotate counterclockwise. Okay. So in physics 1, we would have just said this is a counterclockwise torque. Okay. But we can do better than that now. And it's just a simple right-hand rule. You take your right hand, you curl your fingers in the direction that it wants to rotate, which is counterclockwise, and your thumb points in the direction that of the torque. So in this case, we would say the torque is coming out. Okay. If I did it a different way, so let's say I had another bar. Let me do a different color. If I had a different bar, okay, and the force is going that way, okay, it wants it to rotate clockwise. Okay, so clockwise. So to spin my hand, so my fingers are curling clockwise, and you can see, hopefully, that my thumb, and the best angle there, the thumb is pointing straight down. So that means the torque in this case is going down. So in the first case, counterclockwise, that meant the torque was coming out. When it wanted it to spin clockwise, that meant the torque was going down into the page.